our project, in our project we developed a new allocator that is both scalable and also optionally persistent. And the name of this allocator is LLFree. And this project is a joint collaboration with the Hamburg University of Technology. So let's start with a quick overview of the problem. In general, many memory management subsystems have been developed for single core systems with low memory capacities, and we still see this today in Linux, for example. However, the times have changed. We now have systems with a lot of CPUs that access memory in parallel, and even accelerators like graphics cards that work with main memory. And on the other side, we have a lot larger memory capacities and even different properties like persistency, for example. And all of this means we have more and more contention on the data structures of the memory subsystem, and the memory management in general becomes more and more a bottleneck in the operating system. And this is especially also true for the page frame allocator that manages the physical memory. It now has also to support huge pages. Huge pages are becoming increasingly important for the memory management in the operating system. And it also has to deal with huge page fragmentation. And we see this performance bottleneck in reality if you look at the Linux allocator, for example. In this benchmark, we allocated a lot of pages in parallel, and we see the allocation time, the average allocation time increases dramatically if we allocate on multiple cores, up to a factor of 10 in this case. And in the next few minutes, I will show you our new allocator design that scales very well on multiple cores, especially compared to the Linux allocator. But first, let's take a quick look at the Linux allocator itself and its problems. In general, the Linux allocator is based on the body allocator design. That means we have multiple free lists that manage different allocation sizes. And the smallest allocation size is exactly 1 4KB page on x86, up to 4 MB in the highest order list. And this design already has a significant problem, and that are its extra costs for splitting and merging pages. Especially when you allocate a lot of small pages, you often encounter the situation that the corresponding free list is empty, and you have to take a larger frame from a higher order list and split it in halves until you have the requested allocation size. And this means a lot more list operations, which are especially costly because those list pointers, those next pointers, are spread over a vast memory area because they are part of the struct page in Linux. And those linked lists also have a second problem, and this is that they are not thread safe, so they have to be synchronized when we want to access them in parallel. And Linux uses a single lock to protect all of the free list. And obviously this is really bad because we cannot allocate pages in parallel anymore. And to improve the situation a little bit, Linux uses per CPU caches that buffer recently freed pages for the next allocations, and they do improve the performance tremendously. But they are also overwhelmed if we have a lot of allocations, for example, and they directly lead to the next problem, and that is fragmentation. Those per CPU caches delay merge operations, and instead, so freed elements are not given directly back to the body allocator that then merges them and defragments larger areas. They are directly reused for the next allocations, and this prevents defragmentation. And the body allocator itself also has a problem with fragmentation because it just has no information about how fragmented larger areas of the memory really are. It does not know how many small pages are missing from a huge page, for example. So if only one page is missing from a huge page, then all of the fragments are scattered over the free lists. And these free lists are not sorted, so the allocator cannot prevent those fragments from being directly allocated again. So it cannot wait for the last page to be freed so that the huge page can be merged. So in general, combined with the per CPU caches, the body allocator isn't really able to effectively reduce fragmentation over time. And the last problem of the Linux allocator is persistency. Yes, until obtained memory is discontinued. But we think the persistency property in itself is quite important, and persistent memory will resurface at some point in time. And for that, we need efficient allocators that are persistent and that are able to manage this persistent memory. And the Linux allocator cannot do this because its data structures, its linked lists and logs are inherently not persistent. So it is quite difficult to make this allocator persistent or even impossible. So all of these problems are deeply related to the core design of the page frame allocator of Linux, and they cannot be solved one by one. Instead, we have to rethink the allocator design from the beginning to solve all of these problems. And this is exactly what we did in our paper. We designed a new page frame allocator with the focus to tackle all of these problems. For our allocator redesign, we followed a few design principles. The first design principle is to respect hardware. Obviously, for a page frame allocator, the hardware-specific page sizes that are used for the dynamic paging, so 4 KB and 2 MB on x86, are the most important allocation sizes. And secondly, cache line granularity is also quite important if you want to have cache-friendly data structures. Then the second principle is to avoid memory sharing, which is a common performance bottleneck for multi-core algorithms. So it makes sense to constructively avoid memory sharing from the beginning. And the last principle is careful redundancy. This is more tailored towards persistency. We want to avoid synchronization problems for persistent state, and instead we want to have a single source of truth that is crash consistent. And from these three design principles, we developed the idea to make our allocator entirely log and log-free, or short LL-free. And this has two reasons. The first one is that logs are not crash consistent by themselves. And the second one is logging, although it is crash consistent, it does limit scalability and is slow and also intensifies write varying on the current persistent memory hardware. Instead, we decided to use atomic instructions, atomic updates to update our allocator state directly, with the idea to jump between valid states so that we are recoverable and crash consistent in any point in time. So then let's continue with the architecture of our allocator. In general, the allocator is based on a large bit field, where we have a single bit for every 4 KB page. And the big benefit of bit fields are that they can be accessed by as many CPUs as we want in parallel, and they can just allocate pages by toggling bits with atomic instructions. However, bit fields also have two large problems. The first one is the search for the next free page can take a really long time if we have to scan our entire bit field. And the second one is we can only allocate up to 64 pages with a single atomic instruction. And to solve these two problems, we have designed an index-like data structure above those bit fields. And we have grouped 512 bits together and created a 2 MB entry for each of those 512 bits or 512 pages. Because 512 pages are exactly one 2 MB huge page. And these entries contain counters for the number of free pages in the corresponding bit fields. And this allows us to skip entirely allocated bit fields when we search for the next page. And also, those entries contain in blue flags at the bottom that can be toggled when we want to allocate an entire huge page. And this is much faster than having multiple 64-bit atomics in the bit field itself. So this allows us to very efficiently allocate 4 KB and 2 MB pages. But we still have the problem that when we allocate with multiple CPUs, that those CPUs can end up in the same bit fields or in the same 2 MB entries, and then we have memory sharing and cache invalidation, and this is quite costly. To solve this, we have a second layer above that, where we group 32 of those 2 MB entries together, with the idea that CPUs exclusively reserve those 64 MB entries, and so that they can allocate in their own areas without interference from other CPUs. And this quite effectively prevents memory sharing for the bit fields and the 2 MB entries. We still can, however, have fault sharing in the 64 MB entries. They are also quite small, and they contain also free counters that are frequently updated. So if two different CPUs work on different entries that are, however, on the same cache line, they do invalidate their cache lines. And to solve this, we use the approach of split counters, where we copy the global counter into our CPU local area, and from then on mostly work with the local counters instead. And what those 64 MB entries also allow us to do is to define a policy that specifies which 64 MB area is reserved next per CPU. And with this policy in our paper, we defined it in a way to avoid fragmentation. When the CPU needs a new memory area for a new 64 MB area for reservation, we prioritize already fragmented areas and only fall back on entirely free areas if there are no fragmented areas left. And this quite effectively avoids fragmentation and leads to a nice fragmentation, a nice overtime defragmentation, as we later see. Okay, so much for the general architecture of the allocator. Let's take a quick look into how an allocation really looks like. For the majority of cases, an allocation consists of 3 steps. We first decrement our CPU local counter. If this counter is already 0, we have to reserve a new 64 MB entry. But if not, we can directly continue with the 2 MB entries. And there we also search for an entry with a counter greater than 0. We decrement it, and then we search the corresponding bit field for a 0 bit and toggle it. So in general, an allocation takes, for the majority of cases, only accesses only 3 cache lines. And the free operation is very similar. Here we start from the bottom up. We first toggle our corresponding bit in the bit field. We know which bit from the page frame number. And then we increment the counter of the 2 MB entry. And then as the third step, we either increment our CPU local counter if the current CPU has already reserved this entry. But if this entry is reserved by another CPU or it is not reserved at all, we fall back on the 64 MB entry counter instead. So again, here we access 3 cache lines. And 2 MB huge page allocations are even faster, because for them we do not have to access the bit fields at all. We can just toggle the flags in the 2 MB entries directly. So we only have to access 2 cache lines for them. So then let us take a quick look at persistency and recovery. In general, the architectures of the page frame allocator are self-contained, and thus they are easy to persist. We can just save the bit fields and the 2 MB entries into our persistent memory zone, and they contain all the information about which page is allocated and which page is free. And from this information, we can recover and restore the entire upper level of the allocator, the 64 MB entries and the CPU local data. And also the metadata of the allocator is quite compact. It only takes up 0.03% of the managed memory, which is about 4.1 megabyte for a memory zone of 128 gigabyte. We discuss crash consistency and the persistency properties of the allocator in more detail in our paper, so take a look if you are interested. So instead, let us continue with the performance of our allocator. Here in this benchmark, we allocated a lot of 4 KB pages in parallel. And here we measured the raw performance of the allocator without any of the memory management around it. And we see here the LLFree allocator scales very well. It has consistent allocation times independent from the number of cores that are allocating in parallel at around 50 nanoseconds for allocations and 40 nanoseconds for frees. And this is especially impressive if we also look at the performance of the allocator on persistent memory. Here in this benchmark, we have used second generation Intel Optane memory, and the performance is exactly the same as for DRAM, and this can be attributed to our cache-friendly data structures. Remember, we only access 3 cache lines for most allocations, so the CPU mostly works with its caches, and the extra performance overhead of the persistent memory is entirely hidden. But remember, this is second generation Optane memory that automatically flushes its cache lines on a power loss. So we do not have to use manual cache flushes here. Okay, then also in the next benchmark, we compared LLFree directly with the Linux allocator. And for this, we integrated LLFree into the Linux kernel, directly or entirely replacing the Linux body allocator. This was quite a complicated task, but I think it was quite worthwhile, as we see here, because LLFree is up to 10 times faster than the Linux kernel on highly parallel workloads. And this becomes even more, this difference becomes even more pronounced if we look at 2 MB huge page allocations. There we see that the Linux allocators is about 2 orders of magnitude slower than LLFree on 26 cores. So Linux has a severe performance problem when allocating huge pages in parallel. And we already submitted a patch that improves this. The reason for this was a lot of unnecessary checks while the allocator log is held. So we have a lot of log contention. But even with our patch, the Linux allocator is still 1 order of magnitude slower than LLFree. And yeah, LLFree is down below. Okay, so much for the performance of our allocator. We have a lot more benchmarks in our paper, including some end-to-end measurements. But for now, I want to focus on another nice property of this allocator, and this is its fragmentation behavior. In this benchmark, we initially allocated half of the memory, but in a very fragmented way so that there are no huge pages, no entire huge pages free. And then in every iteration, we free 10% of the memory and allocate the same amount again, so that the overall allocated memory remains the same, but we have a small turnaround in each iteration. And we see after about 40 iterations, LLFree is able to recover entire huge pages again up to the optimum. And Linux, on the other hand, isn't really able to do that at all. So we see our reservation policy that that avoids fragmentation leads to a very nice overtime defragmentation behavior, which is quite nice. So then I'm at the end of my talk. We've started with the Linux allocator and investigated its problems. And then we took a look at our new allocator, our LLFree, that is log and log free, has excellent multi-core scaling, overtime defragmentation, and is persistent on NVRAM. The allocator and all of our benchmark and artifacts are open source, so take a look if you want, if you're interested. And thanks for your attention.